Alright, hello everyone. In this video, I will try to explain the math and algorithm behind the last challenge in this series. Okay. Let me first define the problem properly. So we consider matrices with dimension h by w. Okay, so we have h rows and w columns with entries in the set 0, 1, 2 up to s minus 1. So we have h or s choices for each entry. Alright, now we say that A is equivalent to B, okay, if B can be obtained through a series of column and row exchanges on applied to A. So for example, if I have this matrix 1, 2, 3, 4, 0, 1, okay, and if I exchange the first and the second column and then exchange the first and the second row after that, I would get this equivalent matrix or configuration, which is basically 4, 3, 2, 1, 1, 0. So basically we swap two columns and then first and second rows. Okay, so these are equivalent configurations. Okay, so the task is to count the number of distinct non-equivalent configurations given h, w, and s. Okay, so the input is 3 integers. Right, so how do we go about this? Right? I will try to give the intuition without being too formal. Okay, there is a link below that you can read about every formal definition. But in this video, I'll just try to convey the main idea. Okay, so first let me talk about the notion of permutation. Okay, so a permutation is just intuitively it's just a rearrangement it is just an arrangement of n elements. So we can just index the elements from 1 to n. Okay. More formally, right, a permutation sigma is just is a bijection function that maps n elements to that same set. Okay, so for example, we have the following permutation. We can map 1 to 2. Let's say n is 6, right? We can map 1 to 2, 2 to 4, right? 3 to 5, 4 to 1, 5 to 3, and 6 to 6, okay, 6 to itself. Right. So you can think of this as, why this isn't a rearrangement, right? So you can say this is an arrangement where, first the first element is 2, the second element is 4, the third element is 5, and so on and so forth, right? So again, so a permutation is just an arrangement of n elements. Okay. This is one way to describe a permutation. We just write out which element is mapped to which element. Now, here's a very convenient way to denote a notation, which is called the cycle notation. Okay, so 1 is mapped to 2, right? Now 2 is mapped to 4, and 4 is mapped back to 1, right? So we can write this as one cycle. Again, 3 is mapped to 5, okay, and 5 is mapped back to 3, so that's the second cycle. The third cycle is 6 to itself, right? So just 6 to 6. Okay, so every permutation can be written as a product of these cycles. Okay. Now, why do we care about permutations? It will be a bit clear, but let me define another thing. Okay, so we say permutations are just functions that rearrange n elements. We define the following operation. Let's say this operation. Okay. Now, so let's say sigma and pi are permutations on n. Okay. Okay. Sigma times pi is the composition of two functions sigma and pi. Okay, so basically we apply the arrangement pi. Okay, we get an arrangement, and then we apply the arrangement sigma to that rearrangement. Let me explain this a little bit more, right? So pi times, so these are functions, right? So pi times sigma x, okay, is basically, sigma times pi x is basically the function of the composition of these two functions, right? You apply pi to x, you get some elements, and now you apply sigma to pi of x. And most of you would be familiar with this, but just to be on the safe side, I'll give an example. Okay. So for example, let's say if we have n, we consider easy example where n is 4, right? So let's say this is sigma 1 to 1, 2 to 3, 3 to 4, right? And 4 to 2. Okay, and pi to be 1 to 2, 2 to 4, 3 to 3, and 4 to 1. Okay, now what is sigma times pi? Okay, sigma times pi is to think about. First you apply sigma. Okay, so when you apply sigma to 1, you get 2. All right, and now you apply, I'm sorry, I keep mixing up pi and sigma. You apply pi to 1, you get 2, right? Now you apply sigma to 2, you get 3, right? So 1 is mapped to 3 in this the composition of these two functions. Again, so 2 is mapped to 4 by pi, and 4 is mapped to 2 by sigma, right? So 2 is mapped to itself in this composition function. 3 is mapped to 3 in pi. 3 is mapped to 4 in sigma. Okay, so 3 is mapped to 4 here. Okay, so again you can repeat this, 4 to 1 and 1 to 1, right? So this is the when we define these operations as the composition of two functions. All right. So why do we care about permutations? Now let's go back to this problem. Okay. Let me explain why we are talking about permutation. Now, basically, this is just a rearrangement, of these elements. So, you can think of this as the way to think about this. So this is element 1, column 1, right? Element of row 1, column 2, row 2, column 1, row 2, column 2, row 3, column 1, row 3, column 2. Okay. So these are the elements. Okay, I'll index them by row and column. Now we see this position, right, is mapped to that position, right? So 1, 1 is mapped to 2, 2, right? Now 1, 2 is mapped to 2, 1. Right. So you can think of a series of row and columns exchanges as just a permutation on the matrix entries. Okay, so for example, I'll just write that. Right? So this is correspond to the following permutation. 1, 1 is mapped to 2, 2, right? 1, 2 is mapped to 2, 1. 2, 1 is mapped to 1, 2. 2, 2 is mapped to 1, 1, right? 3, 1 is mapped to itself. 3, 2 is also mapped to itself. Okay, so this is just a permutation, okay, on the positions of a matrix. Okay. Now I'm going to talk a little bit about just barely enough group theory for us to solve this problem. Okay. a group G is a set of elements that are equipped with an operations I will denote it by the multiplication symbol. Okay, so we have the following four properties. There exists an element in this group such that I'll call this the identity element, such that for any element A in this group, right, if you multiply, again this is multiple, if you take A times E, you get A. Okay. Now the second property is, for all A, B in G, right, A times B is also in G. That's the closure property. The third property is that for all A in G, there's an inverse element also in G, such that A times A inverse is equal to the identity element. Okay. And the final fourth property is, that is to say that this operation is associative. Right? So A times B combine, get the result, and times C is equal to A times the result of B times C. Okay, so this is definition of a group. Now we're not going to go into every details of group theory here. I'm just going to define this and say, well, okay, so what are some group, right? For example, the group of integer, right, with the operation addition. This is a group, right? So the set of integers under addition form a group. Two integers, when you add them together, you get an integer, so that's closure. The identity element is of course 0. Addition is clearly associative, and for every element, for example 5, you have an inverse element which is -5. Right? Alright, so so here's a claim that you can treat it as an exercise. The permutations on n elements form a group where the operation is function composition. That we have discussed earlier, right? So you can verify this claim. The identity element is just the permutation that maps each element to itself. Okay. If you have the composition of two permutations, is obviously another permutation. So that's the closure property. For the invertibility property, right, you can note that if you have a bijection function, there exists an inverse function that is also a bijection function. So that's also another permutation. Okay. So now I'll let you check this by yourself. Okay, treat it as an exercise, or you can just believe me. These are pretty intuitive. Okay, so now I'll talk about orbits. Okay, okay. You know, I'll give again, a less rigorous definition or definition just for this exact problem. Okay, so if G is a group, okay, where elements have functions, okay, then on the set X, which is finite, okay, so again, think about permutations, okay, and the orbit of A, okay, for A in X is defined to be all possible values of all possible values. Right? When you take any function of G and you apply it to A, right? So think about okay. So think about what it means in this problem, right? Okay, so in our problem, right? So for example, we have a matrix A, okay, and the the orbit of A is any other matrix B where B can be obtained from A through columns and row exchanges. Okay, so the orbit of an element is all possible values where if we applied the functions in that group to that element. Okay, so this group is just column, the function or the permutations corresponding to all possible column and row exchanges. Okay, so now here's a claim that you can verify for yourself. It's just pretty it's not too difficult to prove that the set of orbits partition X. Okay, so again, here you have a set of functions that act on a set of elements X. Okay, and now the orbit of each of these elements is, so the orbit of A in X, okay, is all possible G of A for every function G in the group. Okay, so now the set of orbits partition X. Okay, think about what it means, right? It simply means that so in our problem, right, the bits correspond to okay, so in our problem, right, this partitioning, right, corresponds to equivalent equivalent configuration. So for example, if you have a matrix 0, 1, 0, 0, right? So the orbit of this, okay, is, you can freely apply any row or column exchange to, a series of rows or column exchanges to this matrix, right? And what you get is, these configuration. Right, so this is, okay, so again you can check the orbit of one of this matrix. You have 2 1s in the first row and 2 0 in the second row. Then you would have the same matrix, right? So that's when you applied the identity permutation. Okay, or you can you can swap the rows, right? That's what you get. If you swap the column, it doesn't change anything, right? So you still get, if you swap the 2 columns, you still get one of these 2 configurations, and so on and so forth. Right? Well, let's check, right? So okay, so now let's do another. So the orbit of 1 1 in the first column and 2 0 in the other is similar. Right? So you can have okay, so again, the set of functions here is, is rows and column exchanges. Okay, so well, maybe let me, well, why not? We are almost, we are already doing pretty much all of these, so why not finishing them? I think I still miss one. Let me see. Yeah. Okay, so basically these are bits, form 7 equivalent classes. Okay, that's what we are trying to count, right? The number of equivalent classes. Now, okay, so Okay, so let x minus g, okay, be the number of let me see how to say it. Be the number of equivalent classes. Okay, so basically, if you want to be more formal, it would just be, you know, so x of g is these sets. Okay, you know, in the sets of all of these objects. Okay. Okay, so x of g is just the set of all possible objects or the number of equivalent classes. Okay, so now that's what we are trying to count, right? This is what we are trying to count. We are trying to count the number of equivalent classes, you know, when the functions are column and row exchanges and elements are matrices. Okay. Okay, so here's what's important. Okay, so this is what called the Burnside lemma. This is the key thing to solve, the key idea to solve this counting problem. The proof is not too difficult. You can read it in the link below the video. I'm just going to state it here. And okay, so G be, let fix of G be all elements in X such that G of X is just X. Okay, so think about, for example, okay, so let's say G is the following function. Exchange the first and second row. Okay, so let's say 2 by 2 matrices. Whose entries are 0 and 1. Okay, so what is fix of G here? Fix of G is, well, you know, for example, this matrix, right? 0, 1, 0, 1. So if you swap the first two, the two rows, you know, they don't, you get the same element. Similarly, 0, 0, 0, 0. Okay, 1, 1, 1, 1. 0, 1, 0, 1. What else? 0, 1, 1. No, this. I think that's it. Yeah. Hopefully, I don't miss anything. Right? So if you apply G to any of these elements, you know, you get the same L, the same element. Okay. So fix of G is just that. Okay. Now this is what Burning lemma says, right? The number of equivalent classes, okay, is equal to 1 divided by the size of the group, okay, the number of functions, times the sum over the functions, G, okay, the size of fix of G. Okay, so let's check. Okay, so let us check. Okay, okay, so this is called the Burnside lemma. Again, the proof is actually fairly easy. It's not too difficult. Okay, you can read it from the link below. We can just check it. Okay, so we know that. Okay, so we consider X to be 2 by 2 matrices. Okay, G to be yeah, this is going to be a bit. Let me see if it's easy to do. Yeah, G can be one of the following. Okay. The first, okay, so the group G, you have the following functions: G1 to be, you know, let's say row exchange. Right, so you can swap to the first and the second row. G2, you can have column exchange. Right. And G3, you can have both. Right? So you can do a row exchange after column exchange. G4, yeah, I think these are the same. Or you can do column exchange after row exchange, but the effect would be the same. Okay, so now let's check. Okay, we know that the number of equivalent classes is 7. Okay, so now let's check, right? So the size of fix of G1. Okay, so when you do row exchange, you have 4 configurations that don't change, so that would be 4. Okay, fix of G2. Okay, it should be the same by symmetry, right? There's no difference here. Now G3, what is fix of G3 here? Okay, so I'm sure these, at least you have these 2 entries, right? Because oh, actually we also have G4, which is, do nothing. Okay, so fix of G3 is 0, 0, 0, 0, 1, 1, 1, 1. 0, 1, 1, 0. 1, 0, 0, 1. And I think that's it. Let me see. So if we do the column exchange, we'll get this. And if we do a row exchange, we'll get this. So that's not the same. Okay, so I think this is it. So let's check. Okay, so 4 plus 4 plus 4. Okay, G4, obviously, right? It fixes everything, so that would be 2 to the 4th. Now, how many permutations are there? You have 2 for rows exchange, 2 for columns exchange. Okay, so let's see. So this should be 4, right? So there are 4 possible functions. Yeah, so then let's see. So this would be 12 plus 16 divided by 4. 28 divided by 4, which is 7. Okay, so this checks out. Okay, so we have 7 groups here, 7 equivalent classes here. Okay. Now, okay, so now finally what we are left with is how to compute the size of these fixed sets. Okay, so for example, let me consider, let us consider the following series of exchange. For example, let's say for rows, we consider the following permutation: 1 to 2. Okay, so what is left is that, given rows, given row and column permutation, how to compute the size of the fixed set. Okay, so let's say we have the following permutation: row 1 to 2, 2 to 1, 3 to 4, 4 to 3, okay, and 5 to 5. And for columns, we have the following permutation: 1 to 3, 2 to 2, 3 to 4, 4 to 5, and 5 to 1. Okay, so let's look in. Let's rewrite this in cycle notation. This would be 1, 2, 3, 4, and 5. Okay. In cycle notation, this is 1, 3, 4, 5, and then 2. Okay, so you can convince yourself that this partitions the matrix into 6 blocks. Okay, so for example, rows 1, 2, and columns 1, 3, 4, 5, rows 1, 2, and column 1, 3, 4, 5. Okay, rows 1, 2, column 2, and so on and so forth, right? So it's the Cartesian product of, these two sets of cycle. Okay, so entries are moved within each block. Okay, so if an entry is in this block, right, it will be moved to another entry within that block. Okay? Yeah, it's probably not too hard to see why, right? Okay, so now let's consider a specific block. Let's say, let's consider a specific block, say, column 1, 3, 4, and 5. Okay, and rows, let's say rows 3 and 4. Okay, so let's look at this entry here. Okay, so what this permutation does is that okay, so you start at row 3, right? So you move to row 4. Okay, so when you move to row 4, you apply the column exchange. So row 4 is now okay, so I'm sorry, so row 3 is swapped with row 4, okay, and column 1 is swapped with column 3, right? So this entry will move right here. Okay, now where does this entry move? Okay, so this entry right here, okay, row 4 will be exchanged with row 3, right? So it will move up. Now column 3 is exchanged with column 4, right? So this entry will be here. Okay, so now so where does this entry goes? Okay, again, if you think about it, right, this entry will, so again, row 4 will be exchanged with row 3, so it will go, and column 4 will be exchanged with column 5, so this entry will end up here. Okay, now where does this entry end up? Okay, this entry end up at okay, so row 4 will go back to 3. Okay, now column 3 will go to column column 5 will go to column 1, right? So this will go here. Okay, so now let's redraw it. Okay, so you now have these 4 elements. Okay, so these 4 elements, this one will come here, this one will come there, this one will come there, and this one will go back here. Okay, so in order for the matrix to not change, okay, these 4 entries must have the same values, right? So okay, so if you apply this transformation, right, and you end up with the same matrix, then these four entries must have the same values. You can do the same thing for these four guys, right? So these four must have the same values. Okay, you can check that this one will be mapped to that one will be mapped to that one, that one will be mapped to that one, and back here. Okay, okay, so that's the picture. Now, okay, so what is left to say is, okay, so there are s possible values for these black dot entry, okay, and also s possible values for these cross entry, okay. um, so that the matrix is the same after the transformation, okay. Okay, and you need to do this for every block, okay, every of these 6 blocks. Now okay, so within each blocks, how do you know how many so here you have 2 groups, right? Okay, so how do we tell how many blocks, how many groups do we have within each blocks, okay? Okay, so how do we compute the number of groups within each block? Okay, so think about this, right? So if okay, so let's say we start here, okay. Let's say consider a block of let's say alpha rows and beta columns, okay. Start at an entry, okay, at row I, column J, okay. So okay, so we follow this path, okay. So after alpha steps, right, we get back to row I, and after beta steps, okay, we get back to column J. Okay, so for example, the row here is 2, right? So after the first step, you get here. After the second step, you get back to the first row, right? Similarly, so again, after another 2 steps, we get back to the first row. Okay, so here we have 4 columns, right? So after 4 step 1, 2, 3, and 4, we get back to the first column. Okay, so we get back to ij, right, after the least common multiple of alpha and beta steps. Okay, so the number of groups is equal to the number of entries in this block, which is alpha times beta divided by you know the least common multiple of alpha and beta, right, which is, so you can check that this is equal to the lowest the greatest common divisor of alpha and beta. Okay, so what does this give us in general, right? Okay, so so for example here, right? How many groups do we have, right? The number of groups here is what is alpha times beta? 2 times 4 divided by the least common multiple of 2 and 4 is 2, right? So, okay, oh yeah, so this should be 8 divided by 4. So then we have two groups, right? So these two groups are the black dots and the red crosses, right? So these two groups, so the color within each of these two groups must be the same, right? Okay, and this must happen for every block. Okay, so so here's the algorithm, right? Okay, so given a row permutation, let's say given a row permutations, with cycle lengths R1, R2, right? RH, I'm sorry, let's say RL, okay, and column permutation with lengths C1, C2, right? Let's say CT. Okay, so we must have the following. So R1 plus R2 plus RL is equal to the number of rows, which is H. Okay, C1 plus C2 plus CT should be W. Okay. Okay. So So with this transformation, right? So I'll call this sigma, and I'll call this pi. Okay. So the size of fix of sigma and pi, okay, is the product of, I from 1 to L, the product from J from 1 to T, and so each of the block correspond to Ri and Cj, right? You can divide it into GCD of I and Cj groups. Okay, and each of these groups you can take on any of these S values. Right? So this is why this is the key formula right here. Okay, so now the rest of the algorithm is to being able to enumerate through all of these possible transformation and compute this. Okay, that would be that will be left to you as an exercise. Okay, how to implement this efficiently. You can see the code that I wrote. Okay, if you're really stuck. But let me stop this video here because it's a bit too long. Okay, so I'll just recap this with okay, so in the end, right, you need to compute the following. So 1 over, how many possible transformations are there? You have H permutation for the rows and W permutation. I'm sorry, H factorial permutations for the rows and W factorial permutation for the columns. Okay, and then you want to sum over all possible sigma and pi, where sigma is the permutation of row and pi is the permutations of column. Okay, and then you want to do the following. Okay, okay. Of course, this will require some basic combinatorics to do, but I'm pretty sure you should be able to do it on your own. All right, so I'll stop the video here. Hopefully, this will give you some idea of how to tackle this problem. All right, see you later.